All right, it's recording. Let's just review. What flow regime are we looking at? Radial flow. And are we looking at a buildup or a drawdown? A buildup. And what happens before we run a buildup? That's part of the buildup. But that's the first thing we see in a buildup. What happens before we start a buildup? Huh? Yes, but we have to have flow. That's what I'm trying to get. Is you can't have a buildup by itself. You got to have some kind of flow. So during this flow period, it's been idolized for this particular problem to have flown for how long? Huh? $2,000 hours. And at what rate did it flow at? 100 MCF a day. So when we look at a buildup, we kind of have to have some information about the drawdown prior to the buildup. Now, we can look at variable rate buildups. We have that powerful function called superposition, which we can use in many cases for drawdowns and for buildups. But for this example problem, hypothetically, we produced the well for 2,000 hours at a constant rate of 100 MCF a day. Okay? So we have the given data was time and pressure. And at time 0, as my comment reads, that was the flowing pressure. Okay? So ideally, we had some pressure initial, and we started flowing this well, and the pressure came down to PWF, and then we build up the well. Actually, we can't build it up higher than it was originally. So that's what our pressure versus time looks like. Now, I think you need a good physical connection to what's going on. We can analyze a drawdown, okay, by itself and get perm and skin. And or we can analyze a buildup by itself and get perm and skin. And we had a little bit of a debate about why we get different perms and skins on drawdowns and buildups, and those are good conversations, but that's not final exam material. Okay. I gave you some software so that we could directly calculate pseudo time. It's covered in our textbook. Okay, and we got that in there. And we calculated Horner time. On a drawdown, if we produced at constant rate, we would plot our pressure versus the log of time. On a buildup, we have to account for the amount of time that we produced. So we have this time ratio that's a function of T sub delta T and time produced. It's a very simplified version of superposition when we produce at constant rate for T sub P. It's a very simplified form of superposition. We're accounting for the fact that at this time and pressure was superseded by this time and the production rate, basically the amount of time it was produced at a constant rate. Again, this, we couldn't use Horner time per se. We'd have to use a more complex function if we had a variable rate history. But our rate history was constant, dropping to 0. Incorrect. We're going to use pseudo-time pretty much. We should use pseudo-time all the time in a gas well. We actually didn't use it in the first couple of examples, and the textbook kind of wants to lead you along. And also, I think one of those drawdowns was like for 3 hours, and so the amount of viscosity and compressibility changes that could occur are not significant. But we could go back and look at the first two and actually do pseudo-time for those. But we should actually, in doing gas test analysis, always drawdown or buildup, use pseudo-time.
So when we use the FP, the pseudo pressure, so the time will be pseudo-time?
As far as I'm concerned, the answer is yes. We always use pseudo pressure. Now, I humored the textbook so that we could match the example problem and used apparent pressure. Remember, apparent pressure was pseudo pressure multiplied by some constant, so it appeared to have the magnitude of units as if it was a pressure, but it has no physical meaning as a pressure. I always prefer pseudo pressure. Now, I like apparent pseudo-time because otherwise pseudo-time would actually have units of viscosity in it. And so I like to convert it back to hours. So if you look at the VB function, it requires initial pressure if it's a buildup. It doesn't require it on a drawdown. It's assuming it's drawing down from initial pressure. But then it's going to calculate viscosity and compressibility at initial pressure and multiply it back in by a constant to get apparent. So even though I don't like apparent pressure, I do like apparent pseudo-time. So that's what we're sticking with. Okay, so we got everything. Everybody's good through column E, aren't they? We got there before. And so column F is just our pseudo pressure. We're just using our VB function, so that's always going to be a function of our composition and reservoir temperature. And our composition is governed by our gas gravity and our 3 common impurities. And then, because we know in advance we're going to be doing some type curve matching. Type curve matching is always delta T versus delta P. So our delta P or delta pseudo pressure is on a buildup. Let's just back up for a second. On a drawdown, it would be initial pressure, initial pseudo pressure, minus the pressure at time. On a buildup, we don't know initial pressure. We've been flowing our well, and we have no idea what initial pressure is. Our delta P is, or delta pseudo pressure, is the pressure at time minus the pressure at the time the well was flowing. So that's why I've got this commented here. This is PWF. So I calculate a pseudo pressure at that pressure at time 0. Then that's pseudo pressure of the well flowing. And then my delta pseudo pressure is my pressure at any time minus my pseudo pressure at the time of 0, which is the pseudo pressure of the well flowing. Okay, and then we can also calculate the derivative. And I seem to be real happy with this smoothing technique of doing it under and over. And then this is not technically correct because I'm plotting it versus the time in between 0.0221 and 0.04. And see, 329 is about halfway. But in actuality, can I just finish this one little calculation, then I'll answer your question? See, I'm plotting it versus 0.0329, and I should be plotting it at a time that's average. But it's not going to become critical. So I mean, in most cases, I'm just letting you know I'm not technically correct by using this approach, but this is just an averaging approach because I get rid of a lot of the noise when I do my semi-log derivative of pressure. Now, what's your question?
Can you just go to the very top one, that's the seat time derivative? I know we just
I'm just really a little bit lazy and don't want, and I'm saving myself a column. I know the outcome has very little effect. If for some reason your delta T was not smoothly running and had a big gap, and then that number I calculated off to the left was vastly different than the midpoint or the time that they actually captured a pressure, then it may affect my analysis. But I'm using that little smoothing thing. Okay, so I set us up to calculate X, which is really T sub D over C sub D, and Y, which is P sub D over delta pseudo pressure, and that derivative. But we haven't done one important thing yet. But let's look at what we have done. We kind of rushed to judgment and said if we do have a semi-log plot, and this is always called a Horner plot. And if you see the word Horner plot, you know it's a buildup because you don't have to use superposition of the previous non-shut-in, non-flowing time if you're doing a drawdown. So we have a Horner plot. We believe, kind of in a rush to judgment, that that's our straight line. And we calculated a perm using our equations in our textbook. And from the slope, which is a logarithmic slope of the latter portion of the data. And then didn't we get to the point where we had calculated a skin also? No, we didn't get to skin, did we? Okay. We'll save that. Okay, so I'm going to insert a column because I haven't done one important thing here. Oh, this is going to be the advantage of not using this computer. As you see, my insert a column fast button is saved. I need to calculate what I'm going to call delta T. I may change it after I look at it, but I call it effective time. And if we look at our textbook, what I'm referring to here is here right after the numeric 3. Now how come I can't, I was going to copy paste this, how come I can't? That's the trouble when I keep changing software and computers. How come, there we go. 1 page, 2 page, save as print. How about copy?
Can you right-click and select a different tool?
Right click where?
Usually, Acrobat, you can right-click and choose a different tool that might not be.
I'm in Adobe.
I've not seen this version.
Yeah, see, I'm in Windows 8 and Adobe. And when I was in Windows 7 on this other computer, I was able to just highlight it. I probably can do an alt print screen. Let's see if that works. I can't find my print screen button. Oh, there is an alt print screen. And it's some magical formula with a space bar, and I can't remember it right now.
You can try to do the snipping tool in the Windows.
The what?
Snipping tool.
Snipping tool. Yeah, where is it?
In the search program of the S. Is it Windows 8?
Ah. Okay. Right here?
You have to have what you want to select already in the background.
Well, that seems to be a problem. Because when I come over to my Adobe, I lose my...
Can you force the toolbar to come up?
I don't seem to be able to. It seems to want to be able to...
Close Excel.
There's my snipping tool. And
Where's Adobe? Do you have like simultaneous modes or something?
yeah, let's see if I can't get them up. You see, I opened it right here, though. So now I got it open twice. But I don't think this is going to help me. See, I'm in the same boat that I was. In fact, I can't even figure out how to close this.
There's probably a shortcut key you can use.
The snipping tool, and I don't know what it is. Okay. You see Adobe? Hmm?
You might want to check the options of the help file real quick just to see if there's a quick shortcut key for a snipping tool.
Shortcut for snipping?
Yeah.
No.
Now open up the snipping tool dialog box that you had there on the taskbar. And click the little help button. Or options.
I don't see anything that's going to help me. There is a function, and I think I wrote it down. I'm not going to worry about it. We can write this down. What page am I on?
Do you have a print screen function in your service?
No. It's something function something spacebar, and I've been told it and I wrote it down somewhere, but I don't have it with me. Okay. Again, I switched from that software to this software. All right, what page are we supposed to be on? We're supposed to be on page Agawall time 132, and I'm on page what? 100? Okay, so here's our equation, and I just wanted to kind of read this. Where's my expand? Here we go. So the Green-Garten type curves, that's what we're using, are based on solution equations modeling constant rate flow, which is a drawdown. However, they can also be used to analyze buildup tests if the appropriate change of variables made is to account for the differences in flow and buildup tests. Now, just like we used Horner time for our semi-log analysis, we're going to use the Aggarwal equivalent time, delta TE, for our buildup. So it is, I'm going to just write it down for myself. It's in page, it's equation 6.103 of your textbook, but it's delta T divided over by 1 plus delta T over T sub P. And when we use this delta TE instead of delta T, we can place our P sub D, T sub D functions on our type curve. Okay, we're going to come back to our textbook. So I need delta TE. And we're going to do it with T sub A. So this equals our delta T divided by, open a paren, 1 plus delta T again divided by T sub P, produced time, 2,000 hours, and I need to F4 that. And so that converted my very first data point from 01311 to 013. Didn't do anything. But toward the end of my buildup, and incidentally, a rule of thumb is you don't even have to use Agrawal equivalent time if the duration of your buildup time is less than 10% of your drawdown. We know our drawdown was 2,000 hours, so if our buildup doesn't last more than 200 hours, we would have been okay. But for these data points past 10%, we'll see that we'll have significant changes. So our last buildup time was I think by the time we account for viscosity and compressibility, changed to 1920, and then that changed to 979. So we have this changes our tail end of our data much more drastically than it does the beginning of our data. This little correction. All right, so now we have a delta TE column. Agrawal's effective time. Now, I'm going to tell you this right now. We'll have a test next week over radial flow, and then we'll start linear flow. And when we're looking at a buildup or in linear flow, we have a different Agrawal effective time. Superposition is reliant on knowing the flow regime you're in. In other words, this time grouping combination is assuming we had radial flow in our drawdown and now have radial flow in our buildup. When we think we have linear flow in our drawdown and linear flow in our buildup, our Agrawal effective time is going to be a different formula. So, I'm going to even add in here this is Agrawal's effective time for radial flow. Okay. Now the other thing that we've left undone before we can jump to these columns is we haven't done anything about wellbore storage. And I don't think we need skin. I'm going to try to do these in the orders that I'd really like to do them in. I normally get perm and skin first, but I'm hesitant. Let's just go ahead and finish off skin. It's not on our path to get our type curve, but let's go ahead and get skin because that's the way we've got this set up. Okay, we need our pseudo pressure at 1 hour. That's off our graph. Right off our Horner plot. Okay, and I'm actually going to plot that point up here. Now, remember that on a Horner plot, T sub P plus delta T over delta T. As delta T becomes large, what does the Horner time become? What? 1. The log of 1 is 0. So it's the y-intercept. So our P star, extrapolated pressure at infinite shut-in. So our time, instead of going from left to right, on the graph is going from right to left. And you can see that we built this well up for a long period of time, so it's almost back up to initial pressure, but it can go a little bit further. So on a build-up, we always get one more thing than we get on a drawdown, and that's an extrapolated pressure at infinite shut-in time. That's a valuable reservoir engineering tool to know what the current reservoir pressure is. Now what we want to get skin is we need pseudo pressure at 1 hour, which is a point along that line. And where is it along that line? It's not an intercept at all. What we have to do to do that is we have to calculate Horner time at 1 hour. And then use the equation of a straight line. Horner time at 1 hour is T sub P plus delta T over delta T. Delta T is 1. So it's just T sub P plus 1. In our case, that's going to be 2001, but I'm going to make an equation. Equals 1 plus $2,000. That's the Horner time. Now, we have a semi-log straight line. And if I do this right and plot it right, I'll end up on this straight line. So this straight line says my pressure is equal to the intercept. We got to be careful with our slope. It's obviously a negative slope. Times the log of our Horner time. Pseudopressure sub 1 hour equals P star, our extrapolated, or, let's just work with our intercept in pseudopressure terms. Yeah, we're getting pseudopressure sub 1 hour. So it's our intercept minus our slope, and I'm pretty sure that it's times the log of our Horner time at 1 hour. And let's plot that. What equation? The equation of a straight line? Yeah, this is the equation of a straight line. Y equals mx plus b. Our intercept is b, our slope, and you can see I had an absolute in here because all of our permeability equations require the absolute slope. So I hope I used a negative sign, realizing my slope is negative. I'm starting up there at P star. I got to walk down that to get a T sub P at 2001. Okay, so now on my graph I'm going to plot that point for illustrative purposes. So I'm going to add pseudo pressure sub 1 hour, and my X value is 2001, and my Y value hopefully is this one I just calculated. And lo and behold, it turned out to be on my straight line. I can still do the equation of a straight line on a semi-log plot. Okay, so it's important to note that anytime we're looking at P sub 1 hour or pseudo pressure sub 1 hour on a drawdown or buildup, it's not the actual pseudo pressure related to the actual pressure at 1 hour. Because sometimes in our time data we may have 1 hour and we might think that that's where we get the pressure that we get the pseudo pressure to use. But it's off the straight line. So I think we can calculate the skin now. Let's go get our textbook.
You have an FM button on the keypad?
Yeah, I got functions.
Alt space FM? Is that
Alt space function. And we'll see if that's a print screen. Is that what you're saying? I think you may get it. And I'll look at it. Alt what?
space bar and FM?
I remember the space bar was in there.
And then FN and space bar, another one.
Alt space FN.
Or just FN and space bar.
Yeah, that works. So just FN spacebar. Okay, so we can get equations if we want them. And the one we just got here, and then when I'm over here, I can probably, how do I crop it?
Probably use a snipping tool now.
I'm not sure what I'm going to do now. I don't want to save it.
Just paste.
What?
It should copy it to clipboard. You should be able to just paste.
Okay, making a lot of progress. Okay, so there's my aggregate effective time. So at least I know I can get these equations in the future. Thanks. Okay, let's go get our skin equation. Skin, I forgot to look for that. We probably get it from our table that's continued forever. Okay, summary of working equations for pressure transient analysis in gas wells. Flow test, see we have a skin here of P star or PI minus P sub 1 hour. And on build-up test, we have this skin factor equation down here. So what's my thing? Function spacebar. And then I can snip my equation. Ah, I lost it. Okay, now I have a skin equation, and I'm ready to calculate skin. Everybody good? Of course, you guys don't have to do this. I'm just showing you that I'm really getting these equations from the textbook. Okay, skin is our constant 1.151. Pseudo pressure at 1 hour is this number right here, minus the pseudo pressure of the well flowing. That's the one I do a rollover on. Pseudo pressure of the well flowing at time 0. Divided by, I believe, my slope. Where am I? Pardon? My what?
The pseudo pressure at 1 hour.
Pseudo pressure of 1 hour, which I just got through calculating and plotting on my graph, minus the pseudo pressure of the well flowing, which is the pseudo pressure of the pressure at time 0. Now I divide it by my slope. And subtract the log of K, which I've calculated, divided by phi mu C sub T RW squared. I'm using their values for mu and C sub T times RW squared. And then I add a constant. And I need one extra parentheses because I need the denominator and then I need the log function. So I got 2 closed parens before I add my constant. My constant's 3 something. 3.23. And then I close everything that's affiliated with my, I don't know why my colors didn't match. I don't know if I got the right number here. Open, I don't have enough parens in here. Open, I got my difference, I got my log, and I see I don't have my 3.23 in the right place. I still don't do it right. Open, open, close, close. I think I'm okay now. Okay, I got a skin of negative 7.9. What's our textbook have for examples? This says 6. Which one are we on here? We're on 6.4. Almost 0. We got a negative 7.9. I don't like it when they put numbers in parentheses. They got a negative number? A negative number less than 1. A small negative skin. So I'm using mu CT average that was given. I didn't calculate my own properties. Porosity wellbore radius, the slope, pseudopressure from 1 hour, and the perm that I calculated last week from the slope of the straight line. The pseudopressure corresponding to the pressure at time equals 0. It'd be this point right here, okay? At time 0 on our buildup is actually the same as the last point on our flow. I got negative 0.7. Negative 0.8 actually. Okay, are we ready to move on? Okay, what I'm after is wellbore storage now. And it says to go to page 134. I'm almost there. And here's what I'm going to use. I'm in table 611, summary of analysis techniques for type curve plots. And we're using delta pseudo pressure versus, it doesn't matter whether we're using it versus T or TA, except for this has got TA, oh yeah. It's okay to use it because we got delta TA. So the equation I want to use here to calculate my wellbore storage is I have rate, temperature, phi, h, c sub t, rw squared, and I need delta T over delta pseudo pressure, USL. USL stands for unit straight line. We'll go back and look at our type curve, and we'll see that on our type curve that wellbore storage is represented as a log unit slope. Okay? Now, we're going to make a Cartesian plot of pseudo pressure versus time. Doesn't matter if it's delta pressure or pressure. The slope's going to be the same. And if we have an early straight line slope, the reciprocal of that will be what we want. Because we're going to plot pressure versus temperature, not time versus, no, I'm sorry. I never meant to say temperature. We're not going to plot time versus pseudo pressure. We're going to leave time as our dependent variable, plot it versus pseudo pressure, look for a straight line. If we get a straight line, then what we see in parens right there will be the reciprocal of that slope. Then we can calculate wellbore storage. So, function spacebar. Yeah, here I am. Now, are you asking a question? Pardon?
Can I ask you a question?
Yes.
Whenever we do the Horner plot and we do the trend line of the logarithmic and
Semi-log.
semi-log, the part that is the linear plot, that's considered our middle time region. Am I wrong by saying that?
We're assuming it is.
Okay, but that's a good
Yeah, we're rushing to judgment.
Okay.
We're going to assume that is because it looks straight. Okay, and I've looked at hundreds of these, thousands probably, and so yeah. Now,
But that's only on a Horner's plot, correct?
oh, well, if it's a drawdown, it'll still be a semi-log plot, except for we won't have to use Horner time because Horner's is a superposition technique to handle the fact that we're analyzing the buildup after it produced. Okay, now what do I do with my snipping tool? What is going on here? New. I got too much. That's all right. And you're saying I can now delete this. And paste. Okay, so the only thing I don't have is I don't have this last term in parentheses. So let's plot pseudo pressure versus time. And we could use remember, we don't have to use equivalent time for the first 10% of our shut-in time. So 2,000 hours is our produced time. So for the first 200 hours, we don't have to use effective time. We can just use our apparent time corrected for viscosity and compressibility. So I want to plot this. I'm holding the control key down so I can capture this twice. And the reason I'm capturing this much data is I already know what the answer is in advance, but we can look at this a little bit later. Okay, insert, graph. And I'm looking for an early time straight line. And let's just make this longer. Let's make this 140. Okay, do you see how it curves way over if I use all the data? But if I just look at the first 8 points, it appears to be straight. Now, I think I have too much data here. It's really hard to look. But I'm guessing my first few data points, first 6 data points are probably a straight line. And one way, let's see, let's put in a shape, insert shapes. Insert shapes. I want to insert a line. Illustrations? Shapes. Straight lines. Okay. So I'm just going to put a straight line in here. Okay. Now I can change this a little bit. Okay. So it looks to me like I got pretty good linearity out of the first 1, 2, 3, 4, 5, 6 data points, and then my data falls away from that. Okay? That's my interpretation. We don't have to worry about being this 100% correct because we're going to check this on our type curve. Okay, so I'm going to highlight my very first 6 points. Pseudo pressure versus time corrected for viscosity and compressibility. Okay, let's get the slope. Here's where I'm calculating everything. I've calculated perm. Okay, let's get RWA out of the way. RWA equals RW times e to the minus s. Is this number going to be bigger or larger than 365? Because it's negative skin, so it's going to see it as if it was a larger wellbore. Okay. Now, do I have a unit straight, what is it called? Unit straight line. I'll call it slope. Early time slope. equals the slope of known y's, comma, known x's. Okay, there's my semi-log slope. I'm sorry, early time slope. Forget I said semi-log. Okay, now I think we have everything we need to calculate wellbore storage. Par-
What, can you show your RWA?
RWE to the minus S. We've done that on every example so far. Okay, I think I can calculate C sub D. Dimensionless wellbore storage. Can I show you what? The what? What? I haven't plotted the line on my graph. The new graph that I made? I don't know. Here it is right here. That line I just drew in there manually to see which data I should select. Because looking at a flat surface like that, now if I've got it printed, I can roll the paper and look and see which data points line up this way and where it deviates. But on a flat computer screen, I can't see it, so I have to slap a line on there and play with it to see which data points should be linear. So that was a manual shortcut technique. I could, now that I have a slope and I could get the intercept, I could plot my line on there. It's not that critical. It's not going to be too much different than the blue line I just drew on there. The blue line helped me identify which points not to use. You see that I'm not using these points over here. Okay, I got a C sub D, and I got an equation for C sub D. Equals 0.375 times the rate I'm guessing the temperature's next. Converting it to absolute. I was right. Divided by, I'll put this in parens, phi h c sub t rw squared. Phi times h, what's the next one? C sub t. Times rw squared. I'm not done yet. Phi h c sub t rw squared. Now I got to divide by this slope, but I can just put that in the denominator, in that open paren there. And I get 9.14. Okay.
Can we use the other one? Change your theory. Change your pressure. Why did you select this one? Is there a reason? Or can we use any other one?
If you made a log, that's a good point. Let's review this. I'm glad you asked that. I'm always looking for more things to do in class. Let's make another plot and get that same number. Okay, this is a Cartesian plot, right? I'm going to delete, well, I'll leave that line there. Let's make it a log-log plot of delta T versus delta pseudopressure. I've already got delta T, but I don't have delta pseudopressure. I got pseudopressure. Let's plot pseudopressure instead, okay? And I'm going to have to get rid of the first point. I'm going to have to convert the 4 to a 5 because I don't have any delta pressure at time 0. I had a pressure at time 0. I could actually, the reason I chose the plot I chose to get my data from is I have one more data point. When I go this way, I don't have that first data point because I can only work with delta pseudopressures. But let's do it this way. So now I've shortened my data sequence, and I'm going to make it a log-log plot. And I have to get rid of some of these cycles. Number, what am I looking for? Labels, tick marks. Where's my min-max? Here it is. Okay, I want to go to my Y. Here we go. And I don't need 1. Maybe 1E7. There we go. I think I'm good enough right now. Now, what I could do is move my y-axis over to the minimum. That always looks a lot nicer. Format axis and change it instead of going through 1. Axis value of 0.01. There, my graph's looking a little bit better now. And then the unit slope on a log-log plot always goes, doesn't matter whether I drew this square or not, always goes through 1 square. It doesn't matter that I'm skewed. You see how my line goes through the box? Upper right-hand corner and lower left-hand corner? That's unit slope. Okay? Now, you see how I can transfer that and see how I get the right points? Now let's increase this back to all my data points. I'm adding a 0 on my data. Now I have all my data, but now let's look at a unit slope again. A unit slope on a log-log plot always goes through 1 cycle. And I can get it through 2 cycles. Okay, I'm pretty close to, see how my line goes from 1 to 100 and goes 2 cycles that way. Do you see how my line is unit slope? Now let's transfer it over here. Okay, so this would have been a more thorough approach to finding my unit slope straight line. Okay? So again, my first, second, third, fourth, fifth data point, all on it. My 6th data point slightly starts to deviate. This is my buildup, okay? Because that first 5 data points are on a unit log-log straight line, it's telling me it's wellbore storage. Okay? And I should have done this first. I'm really glad that you asked the question because this is not a rush to judgment. I'm confirming that these first 6 data points are wellbore storage. the slope of that line, or any delta P, or excuse me, any delta T, delta P on that straight line should be the same number. Okay, let's just delve into this just a little bit more. Delta T over delta pseudopressure. I'm telling you, for the first 6 points, they're going to be the same. I'm going to borrow column A. Delta T divided by delta pseudopressure for the first 5 or 6 points are going to be the same number. They're going to be huge. Made a liar out of me. Oh, delta pseudopressure. Ah. Okay, 34, 35, 35, 35, 36. Okay, see how they're basically all the same number. My regression analysis just cleaned that up and got me a best fit of that data. So the way we used to do this with tracing paper, etc., is we would just pick any delta T, delta P point on that, and we would have that number. That's the reciprocal of our slope. So as you see, they're about all 0035s. If I just take 1 over that middle number right there, I'm not going to need that many significant digits. I get 282,000, or was that 282 million? And instead of 282, from my regression analysis, I got 276 million. Does that all tie together now? But this is based on regression. The other one was just based on a point value. But that's where that definition actually comes from in our equation. Any delta T over delta pseudopressure on the unit straight line. But the way I do it, I just plot pseudopressure versus time, find my early straight line, find the slope, and this term in parentheses is the reciprocal of this slope. So I put that slope downstairs. S20 in my equation is the cell above it. Okay, does that drive it home for you a little bit better? Okay, I got wellbore storage. Right here. 375 rate times temperature, absolute, phi h c sub t rw squared. And then I could have used that number I've got over there off the any delta t over delta pseudopressure on my unit slope, or I actually did a regression and got the slope of my straight line. D, fourth. Which first? This is when I first solved the problem.
Not the USL slope, but the slope.
You mean for my?
Yeah, I just want to make sure I have the same. Thank you. So, when we do it, it's okay if we do it your way, or we don't necessarily need to use the delta.
I tend to do things the way I can get things done the fastest with a lot of experience. The best way to do it only came about because I was prompted to do it the right way. Either way should give you the right answer. And we're taking a roundabout tour. We've now established that we're now guessing that we have a middle time region straight line that we can get perm and skin from, and that we have an early time, but that's not really a rush to judgment because we've just proved that it really is a wellbore storage line because it's unit slope on a log-log plot. Very diagnostic. And then we'll tie this together because if we did pick the right middle time region, then our data should display properly on a type curve. And then we'll talk about going backwards, when and where we could start with the type curve and work toward solving for perm, skin, and wellbore storage. Okay, so get some of this stuff out of the way. I need two numbers here. I need a number. I don't know why I did midpoint. Oh, match point. I need the ratio of time and hours to dimensionless time to put my data on a type curve. Don't I have my type curve here? Here's my type curve way over here. Let's move a couple things around here. We're done with wellbore storage. We're really kind of done with our Horner plot. We're done with some of these equations. And I'm really ready to work with my type curve. It's a bit much. So on my type curve, I got T sub D over C sub D, and it's a constant multiplication to get time and hours to dimensionless time and C sub D. Let's just do this two ways. Let's do it trial and error, and then let's calculate the number. So I'm a good guesser. I'm going to guess that when I've reached my Horner straight line, it's going to be about 2,000 on my dimensionless scale. Do you see how I'm making that guess? When I hit my Horner straight line, my derivative goes to 0, doesn't it? That's when my middle time region should be obtained. So I have this data highlighted. That data highlighted was my wellbore storage, and this data highlighted down here was my Horner straight line. So at about 96 hours, I should end up at 2,000. I'm just guessing. I can change my guess. So I want some number up here so that when I get 96, I think I'm in the right column. I should get 2,000. So this number should be about 2,000 divided by 96. And then if I multiply all my TAs, I hope I'm on row 5, times that constant, F4. I'm just guessing that number. Later we'll calculate that number. Okay, and I'm not going to worry about it too much. Okay, likewise, have I calculated a pressure derivative yet? Yep. Okay, my pressure derivative at the end, remember all my data's all my data is, at the end, is middle time region. So its derivative should be 0.5. This, in fact, is 0.5, where all these dashed lines converge and become level is 0.5. On a dimensionless type curve, where they become flat, has a numeric value of 0.5. So my derivative data here at the end, and you can see they're all fairly the same because my derivative should go flat, should be about 0.5. So this number here, to multiply these numbers to get 0.5, it would be 0.5 divided by 60,000. And then if I multiply all my, this constant's true for my pressure and my delta pseudopressure. I like this because we're just going to play here. Equals this number, F4, I got to hold this F4 down, times my delta pseudopressure. And my y prime is going to use the same number. This isn't a normal way you would work this problem, but I'm doing this for illustrative purposes. We don't actually have a p prime for that cell, but that's not a problem. We'll have it later on. Okay? And if I got that right, I should end up with numbers like 0.5, and I didn't. What did I do wrong? I'm off by a factor of 1,000. Now my numbers are closer maybe to 0.5. Yep. Okay. I was off by a factor of 1,000. So now I have this divided by 60 million instead of 60,000. I'm guessing, I'm playing, okay? We actually have the wherewithal to calculate those numbers. But what I'm actually showing you is what we can do, what the other way to solve this problem is to trial and error these two numbers until we can display our type curve in our data so that we get a good match. And when we do and know those two numbers, we can back out perm, skin, and wellbore storage. Okay, let's plot our data. Add. This is why I like to put my example problem, or the name of my well, or whatever it is, somewhere in here. And my X data is my dimensionless time data. And my Y data is my dimensionless pressure data. I believe it's there. Okay. And then I'm going to add my P prime. I'll just call it derivative. X data is the same. And the Y data, incidentally, I always click that and hit delete and get rid of that thing there, that little thing that thinks I'm a bar chart. And I'm starting in the cell, oops, I'm starting in the cell that doesn't even have a data point. Oops, no I'm not. Starting in this cell that doesn't have a data point, even though I can't see it. And I'm going to get some kind of error message because I got some zeros and I'm making a log-log plot. Okay, let's see how we look. I may not see anything. Okay. I made some mistakes because our time scale should be the same. This says it's I5, and this one is J. Okay, see, I got two. I used the wrong scale for one of my X's. My time scale is J. Which one of these had J? That has J, that's right. This one's supposed to be J. I don't know what I was. There we go. All I did is multiply my times by some arbitrary number and multiplied my pressure and my pressure derivatives by the same arbitrary number. And I estimated what those are so that I'd end up with about 0.5. And let's play with them a little bit and see if we can't get a little bit, oops. Let's see if we can't get just a slightly better match. How do I want to do this? One thing, my time derivative, I should be able to make it smaller because I should move my unit slope line over to the unit slope on my type curve. Do you see that? This data right here should be on the left wall of my type curve data. So this number's too big. It's 20. Let's change it to 10. It's still too big, isn't it? I'm just working with this, and I'm going to have to make this just a tad bigger. Okay, I need to move this data where both the derivative and the pressure term are the same, where they're overlapping, the green and the blue are overlapping. That needs to be on my left wall. Let's make this 1. Too much. 2. Ooh, that's pretty good. How about 2.2? All right. My initial guess for my pressure derivative, or my multiplier for delta pseudopressure to dimensionless pressure, was fairly good. And that's because I knew that I had to get to 0.5 right here. Okay, so now you have your first type curve match.
Where did you get that curve from? What is that figure? What?
It's in, were you not here last week? In content, there's a spreadsheet called type curves. And I have like 8 type curves that we'll use for the rest of the year.
What's the source for the image, though?
Huh?
What's the source for that image, though?
Well, there's one in your textbook, but it's not in color, and it's not as nice.
I mean, I downloaded the one that you posted on.
The one that's called type curves? Yeah. Well, there's several tabs. I think it's like the second tab or third tab. You can just copy paste it over.
Can I see your TD or CD function? Your column.
It's just my adjusted pseudo time times a constant. But to answer your question, these used to be hot things at SPE meetings. Every time a new type curve came out and a new speaker presented it, they were stacked and printed. And so I have a collection of those. And then I went to the scanner and scanned it and hung it here. Because the one in our textbook is very shadowy. But we have a Greengarten type curve.
This is in a journal article somewhere.
Not clean. Not clean. No. You're not going to, unless you got gray hair, you don't have a clean copy. You had to have been around when the paper was published, because in addition to the paper that was presented, and back then we used to present on 35 millimeter slides. Okay, I know I'm really telling my age, but I used to give SPE talks on 35 millimeter slides. We had to have a certain blue background, and we had to have all these other things. But then if type curves were huge, because you could always just plot up your data and slide your data until you got a match. Once you got a match, you basically got that X and Y, and you're going to see, because we're going to calculate that X and Y, because we know what they are, because we have all the inputs for them. But we used to go the other way around. We get our type curve match, solve for our perm, solve for our skin. But you had to manually plot with tracing paper. A lot of fun. You could only do like maybe 1 or 2 wells a day. Now, if you're working for a major company and using advanced software, you better be able to do 50, 60, 70 wells a day. Okay, my plot's not too bad as it is right now. Let's slap it over. Let's do a couple things to it. Let's expand it so I fill out my... I'm doing this so I can get the biggest image possible. Okay.
Why the R derivatives are converging into a straight line?
What's that?
This type of graph, the R derivative curves, they are converging to a straight line.
The green data?
The data say we have the that you got from this type of chart. This, if you see the derivative, on the derivative graph, they are converging to a straight line.
Yeah, that's 0.5.
But is this always the case, or they can go up and down, or which way?
Do you notice that my last data point dips down? That means I could see a boundary. But while it's on a straight line, it means that I have infinite acting radial flow.
It means it is telling that we are seeing the radial flow.
Yeah.
We have not attained the boundary.
This is called a storage skin type curve. Okay? If I was just going to do radial flow, I would just have one curve. But since I can have radial flow with different skins, I have a family of curves. And then on the left end, I'm also handling wellbore storage. So these are all the situations I can have with changing wellbore storage and changing skin. I get these curves. Now, the blue data would be harder to match than it is right now if I didn't have the derivative match. You see how the derivative match, knowing that if I have radial flow, I'll be hardwired into that 0.5 value. And if it deviates from that 0.5, I've hit something beyond. Usually it curves up rather than down. But I don't see anything in my blue data that indicates I see a boundary. The derivative function is a lot more sensitive to change. Now, also, remember I kind of cheated in that my derivatives are jumping. I mean, I could try to make those more accurate. Let's do that. Here's the column I borrow, column A. Okay, let's make this time equal to the average of this number and this number. Okay? Because that's where I'm taking my pressure derivative, above and below. So instead of using my, let's just get rid of that first zero. Instead of using 0.0195, let's use the actual average. Okay? And then I got to make sure these numbers actually appear. And we'll copy that equation down. Okay? And I saw a little bit of a ripple effect. Now, it looks a little different to me, but I don't think I would change my match. I think I got a pretty good match right there. Fairly so. What it took me about 3 or 4 iterations to get a pretty good match. Now, you know, there's no rush to judgment. I never assumed that I had a unit wellbore storage line. I never assumed that I had a middle time region. I don't have to make any assumptions. I'm not using H, porosity, compressibility. I'm using nothing but time and pressure data to get this match. That's what's important about using type curves. I can get to the result for both storage skin and perm without making any beforehand assumptions about my flow regime. And if I don't match at all, maybe it's because I got linear flow and I need a different type curve. So
From the discussion, this type of chart is not accounting for the boundary
no,
impacted section of the data. This is only accounting for the
this is an infinite acting radial reservoir.
early time region and the middle time region, not the late time region.
There's no late time region on this type curve. It's a storage skin type curve. Storage is early time. Skin could happen, but it's an infinite acting radial flow. There's no boundary effect shown here. There's no late time region, but you can see if there's late time region in your data because it will depart. Especially you'll see it on the derivative curve will depart from that 0.5 value. And there's a possibility that my last 2 data points are going south on that.
These type curves of the homogeneous reservoir.
Yes.
Can you repeat the steps for plotting these the data you plotted on the time curves?
You mean you're interested in doing this now? Now that it looks so pretty?
Most of us are not following.
Let's just take a break and everybody get on this page right here. I'll pause our lecture.
Yeah, some car can see how to for the wire front.
This is important. Both the y and the y prime are multiplied by the same 833 that you see there. See that? The y prime is and the y. There's only one value. It locks that difference between on our data plot. It gives you a lock. This is the power of this analysis is really in the derivative function. And again, I'm going to repeat, everything in column L and below and before has nothing to do with any reservoir parameters or properties. Wellbore radius, porosity, skin, or anything that we've already used to calculate perm skin and wellbore storage. I can get myself on this map with just pressure time data.
So the 2 initial guess of the parameters, we just guess it, and we want to make these 2 columns best fit the type curve. The initial guess 2.2 and 8.3 that parameter. How can we estimate these 2 parameters?
Well, you saw me estimate them. I had already done a Horner plot. I already thought I had middle time region data. That middle time region data should have a derivative dimensionless of 0.5. I saw that my actual physical dimensionless or dimensional derivative was a very large number, but it does appear to be flat in this region. Okay? So I ratioed that to be 0.5 divided by that number. 55 million, 65 million. That was my guess, just to get me on the same page. And then I tweaked that number.
Okay, I got it. Let's see your y prime again, your formula.
It's that same constant. I only use the constant once, so I'm the y-axis constant. And then it's my p prime. And my p prime is my semi-log derivative. Ah, I got a problem here. I didn't use viscosity adjusted time.
Can you put that on the lecture?
Let's see if it even has any effect. It should have only affected. I would say that I have to move my time maybe a little bit. Let's just play with it a little bit.
Would you mind turning your thing?
We're splitting hairs. It's not so much I'm trying to get on my unit slope. It started to bother me that I wasn't on one line the whole time on my blue data. I'd say it's possible that I changed 2.2 to 2.15. You know what? We're going to calculate those numbers after the lecture starts. We're actually going to calculate them. We already have the wherewithal to calculate those numbers because we already have permanent skin and multiple storage.
Where your initial guess of 20.8, I know how you fixed the graph to try to fit that number, but your initial guess of like your PD and your X, where did those come from?
Let's just start over. I don't know any idea where they are. I got to get my data on the plot, okay? Let's say, how about if we guess 1 and 1?
Okay.
All right? Can you make that guess?
Yeah.
Okay. Do you notice that I'm not on the plot? We're not on the same page.
Yeah.
Okay? My numbers are such that my time not so much because I go to small numbers to big numbers. But you see, my delta pseudopressure numbers are huge, aren't they?
Yeah.
And so they're way north of my plot. Okay? Let's just do it without any ability to estimate. So I got to make this, let's say 1e minus 6. Ooh, I'm on the same page.
Okay. So this
Okay?
is
What do I do now? I got to make that even a smaller number. See? Now I can maybe start shifting my time over. Instead of 1, let's make it 2. How about 5? Oops, I didn't put it in the right place. Okay, I applied some intelligence to get on the same page immediately, but you don't even need any intelligence. You see what I'm saying?
Yeah.
You can eventually get there. So I think I ended up with like 10. And then I can see that I'm kind of flat with my green data and it needs to come down to that 0.5. So that's a whole log cycle. Okay? So I got to add another 0 in here. Okay? But now my time multiplier is too big. I thought we had 10 before. Once I get a pretty good pressure derivative match right here, and I'm going to play with that. So instead of 1, this is a multiplier. Let's make it 0.8. See, that's not looking too bad. 0.8. That looks about as good as I can. Then I'm going to come back and work on my time. 2.5. 2.2. Okay, so I can be a monkey and get this to work eventually, because if I'm not on the same page, I got to figure out what magnitude I get on the same page, and then I can just tweak in. Now, if you're using If you're using rate transient analysis from FETKI or some of the other softwares, you'll get a little hand. You'll put your finger over the data and you'll get to just move the data. You don't have to guess the X and guess the Y. You get to move the whole thing at once until you get a match. You can do that with transient rate analysis and transient pressure analysis.
Does it supply you back a value once you do the graph?
Yeah, as soon as you give the value, it'll give you a perm skin and storage. The problem with those softwares is they don't apply to the wells we're drilling today. So they've mastered radial flow. But unless you're working the Gulf of Mexico, you're not working radial flow. You're working multi-frac horizontals and you're working linear
So I'm
flow.
going to say that's because we're just in the basic premise that your radial flow is coming from a vertical wellbore. We're normally doing horizontals.
We're drilling horizontals and we're fracking, so we always have linear
We're just
flow.
linear flow.
Yeah.
But after a long time, wouldn't we act like
No, it won't. No, it won't.
not like a horizontal work where we have a light radius?
Look at my guy Bakken shale holes. Where's my other one? Oh, I know, it's back here. Okay, I'm going to turn this back on for a second. This is jumping ahead past radial flow. This is jumping ahead past linear flow transient pressure analysis. We're in chapter 9 now, and we're talking about transient rate analysis. Okay, I only have this slide because in the Bakken Reservoir, we had a drilling boom in the 90s. Do you see that spike halfway through the graph? And you know what? We didn't know how to drill horizontal multi-fracs. And the price went down, and all those wells were uneconomical. And then we had another drilling boom starting at the beginning of this century. I only have this graph because this well was, I'm going to show you, was not offset for 20 years. Okay? This is the production data for that well. Each one of those points is a month. Okay? So there's 120 points on this because this is 20 years of production history. Now, if this is a vertical well, so I'm now emulating the well and the vertical frac. And flow is linear. Now, if flow started to become radial, you would leave that straight line and bend to the right. Can you show me, after 20 years, where it bends to the right? I think in different reservoirs the answer is different, but every reservoir I look at, it never breaks to the right into elliptical flow and theoretically eventually into pseudo-radial flow. It just doesn't happen.
On this particular graph, what happened in the beginning?
The well was not on pump. And so the slope of that is against some delta pressure. The second slope is against the delta pressure of nothing because you got a pump. The first slope is proportional to a head of pressure. So they let it went like this, but then the well killed itself, so then you put a pumping unit on. Yeah.
Definitely showing my ignorance here, but can you clarify the difference between what you mean radial and linear flow?
Well, this is good because we're going to be leaving radial flow and going into linear flow. But looking down on the world, our wellbore looks like this. Okay? And if this whiteboard represents the reservoir we're producing from, and it has a higher pressure from here, your flow streams look like this.
Right.
And your isobaric map looks like this.
Okay.
And we call that radial flow.
Okay, got it.
And it turns out that anytime you're plotting variables like pressure when you build up a well, pressure when you're drawing down a well at constant rate, is that if you plot the log of time versus rate or pressure, we did reciprocal rate, on a buildup it's going to be, we're going to have straight lines. So there's this mathematical fallout that we're always going to get a semi-log straight line. So basically, radial flow is a semi-log analysis technique. Now,
Radial flow, is it like, I guess I understand the basics. Is it really based on that principle of vertical and your isobaric
yeah,
pressure range?
yeah.
What if you just perfed on one side? I mean,
How about if I had a square wellbore? My isobars would look the same.
okay, so, right. So it's the iso,
Yeah,
it's the
yeah.
isobars.
A lot of people refer to this as the point source solution. If you're doing a partial differential equation to solve the diffusivity equation, this is called a point. It's a point source. So it wouldn't matter if you had one perf sticking out one side of a pipe. You might get some kind of hemispherical flow for the first few seconds, but before too long, you're going to have a radial isobaric map. Looking down on a well that is fracture stimulated treated, the reservoir doesn't even see the well. It sees the fracture face. Because we prop this. And so it has 100 to 1,000 to 1,000,000 times the permeability of this formation. And so in an infinite conductivity fracture, which we're going to discuss in flows, it literally does not see the wellbore because it assumes there's no pressure drop from here to here, especially compared to the pressure drop from here to here. Now, when we're looking at this, we throw logarithms out the window. Reciprocal rate and pressure tend to move as the square root of time. So our x-axis for most of our plotting period things in Chapter 6, transient pressure analysis, are going to be the square root of time. In Chapter 9, for transient rate analysis, we'll find that cumulative production actually works better for finite conductivities. When these fractures are less than infinite, when they're finite conductivities, then cumulative production is our best dependent variable. That's all getting ahead. I've just finished the course. All I've got to do is fill in the blanks. Okay? Yeah.
I'm sure you said this, but what exactly are lining up these values on this chart? What is that telling us?
Well, it tells us we have the right model. Okay? If we couldn't get those curves to line up at all, then our data and the model that generated that analytic solution have no fit.
So it's just about fit. It's not telling us a specific value?
Yes, it does. It tells us if we can use the textbook equations right now and calculate perm, skin, and wellbore storage.
Okay, so we use these values to get, so could we use it as kind of a check to see?
Yeah,
if we did
and that's the way I'm going to use it.
Okay.
That's the way I'm going to use it. I'm going to leave it to you for your next exam to do the last thing is to use to match it first and then calculate perm and skin. But I'm going to go backwards. Whatever we got for fits right there, I'm now going to calculate them because I have the wherewithal because I've already calculated perm, skin, and wellbore storage.
I thought it was giving us that, and I'm like, mine do not match up. Does that make sense? We use those values to put them in the equations for.
Yeah. So remember that they're parenthetically match points. It's the ratio of time to dimensionless time. It's the ratio of pressure to dimensionless pressure. They're called match points. But if we look at our...
Like MP, is that for each one of those?
Yeah, match point. So yeah, I'm glad you asked that question because A, it tells us we have the right model. And it tells us that we do, in fact, have a middle time region. Anytime our derivative data is sitting on that 0.5 line, we have a middle time region. So that we've already verified that the data we selected for our Horner straight line was correct. Okay? And because some student tasked me, I actually made a log-log plot and saw that it was unit slope. But if I would have tried to get away with just a Cartesian plot of pressure versus time, and it wasn't really wellbore storage, I would have found out here on the log-log type curve. But I've basically verified, and now I'm going to finally verify it numerically because I should be able to calculate all these values, or both these values, this 2.2 and this 0.809. So let's calculate 2.2. I could use this equation right here, but I think there's a little bit better one. Interpretation of pressure match point. Here's this one. I'm looking at the lower right in table 611. The lower right hand equation is for pseudopressure versus time. So here's perm, H, and we have, by trial and error, we'll work this both ways. Okay, let's. Here's a way to get perm from our match point that we just got trial and error. Function spacebar, huh? Okay, now we're going to calculate perm from our type curve. I'll put it right next to perm that we calculated from the Horner plot. How's that? Perm equals 1422 times the rate times reservoir temperature. No one's ever going to make a mistake again about adding 460, are they? Divided by H. Times P sub D over delta pseudo pressure match point. Now, there's always a possibility I have this upside down. But I think that's this number right here. P sub D over delta pseudo pressure. That's how I converted my P sub Ds. And let's see what I get. I get a slightly different number. Okay. Now, I can get exactly that number by adjusting my pressure just a little bit. And that's the way I normally do it. I get my 285 from my Horner plot, and then so the other way to go here is to calculate what my match point should be. Let's do that. I'm going to calculate P sub D over delta pseudo pressure match point using the known permeability that I have. Okay, you can see I'm working this both ways.
You're saying the one that we calculate first, the 0.0285?
This is set up to solve for K. But I'm going to move H over to the left. I'm going to divide by 1422 QT, and I'm going to solve for P sub D over delta pseudo pressure match point. And I'm going to get a number that's very close to this number right here. Okay? And let's use that number and see how our match looks. So, K, I actually like the K that I'm getting from the Horner plot, times H. Oops, grabbed the wrong cell. Divided by 1422 times the rate times the reservoir temperature plus 460. And I get 6.2 times 10 to the minus 9th instead of 8 times 10 to the minus 9. Let's just use that number I just calculated. And let's look at our type curve. Where is it? And I would definitely have to move my time shift over because I'm not on my unit. See, I brought it down. So now I have to bring it to the left. Let's just do that arbitrarily with our time. Okay, that's our 2.2 number. And I got to make that smaller. Let's make it 2. That's not small enough. I'm going to make it 1.9, 1.8. Okay, that's not even enough. 1.7. Okay, that's not bad. Now it's the same data pattern, but I've moved it over because I'm honoring the perm I've got it from my Horner straight line. So one of the things with type curve matching, there's not quite as much uniqueness as there is from picking one from a Horner straight line, except for now I have a new problem, and that's that the data appears to fall away from my 0.5 derivative constant. And could be a number of reasons, but it still looks like I have some Horner straight line data, let's say from 3, but avoiding my last 1, 2, 3, 4, 5, 6. I don't know if I'd use my last 3 data points on my Horner straight line. Let's just milk this problem here. So I am going to not use these data points. My slope and intercept line probably went from 24 to 34, and I'm going to make them go from 24 to 31. (24 to 34), I'm going to change that to 24 to 31. And that perm's going to go from 285 to 288. It went up a little bit. I got to change my intercept also. That'll only change my skin. It won't change my perm. Because I changed my perm, I changed that match point, and I think, look pretty good. I could move my time over a little bit, but it doesn't look too bad. I may not want to use all that data on my Horner straight line. It looks like my derivative tails away. And I do have my derivative data right, don't I? Remember that during the pause, I changed my derivative data to be my average of my apparent pseudo time, because that's where I'm calculating. That's the average between those 2 points is where I'm calculating my pressure derivative. I think I'm okay on my time scale. Okay. We're halfway there. I've gone both ways. I've calculated my perm. Oh, look at this. Well, once I set my match point equal to the one I calculate from my perm, then the back calculated perm will automatically match my calculation from my match point. It's a circle now. Let's do the same thing for time. Where is my match point for... These are all linear. Oh, here it is. This last one. I'm here. This bottom one is pseudopressure versus delta T. And I can solve this for C sub D from my match point or vice versa. So I want this equation right here from table 611 again. So function spacebar Pardon?
Which CD did you use? Did you use the first one, the interpretation of unit slope, or the definition of CD?
Previously or what I'm doing right now?
Oh, never mind.
Okay. Right now I'm going to use pseudopressure versus time and use this equation right here. And I want to use this equation to calculate wellbore storage. So I currently have a delta T over T sub D, C sub D match point. That's what, I think I may have, this is the one I may have to reciprocate because I actually have the reciprocal of that. I have what I multiply delta T's by, okay? So I'm going to have to be careful here because I'm going to divide instead of multiply. But if I was going to calculate wellbore storage from my type curve at this point in time, and compare it to the 9.41 I got, I would use this equation. Okay, remember we got C sub D utilizing perm and all of our reservoir parameters and our unit slope straight line. Now I'm going to use it from our type curve match. Equals 0.0002637 times the perm divided by phi mu C sub T RW squared. I've covered up phi. I'm going to close that because I've covered up my numbers. Okay, I got phi now. Now I'm going to go back and edit my equation. I still need to add phi into it in this denominator and RW squared. And I still got RW squared covered up. So let's edit it one more time and get RW squared. Okay, I got my constant. Okay, now I have to multiply it by my I'm going to divide. I'm going to divide by Oh, I forgot that I was going to use this tonight. I'll run up and get my battery. I want to divide this by what I use to convert my time to my 1.7. Okay, maybe I shouldn't have divided. Maybe I should have multiplied. Okay, I should have no, 9. I'm not even getting close. What am I doing wrong here? I'm pretty sure I'm supposed to divide. 5 mu c sub t rw squared rw is 012 012 squared. We're getting the same thing. And I'm pretty sure we're supposed to divide by that. Let's pause there, and I'm going to go get my power cord. I forgot that I wasn't going to be on that machine. I'll be right back. Anybody solve my problem yet? How come this didn't take it? Okay, I'm not going to take this off pause until I figure out what I did wrong here. If I don't do anything, delta T over T sub D. One more. Okay, the way these are traditionally set up, you see that P sub D, the dimensionless pressure is in the numerator, and the delta P is in the denominator. Over here, the delta T is here, so if I would want to divide by this number instead of multiplying. So let's,
Did you resume the recording?
just to accurately represent the labels, I'm going to say this is equal to 1 over 1/7. This is just my latest match point. And I'm going to divide by that number instead of multiply it by it. That should give me exactly the same result. I reciprocated it, now I'm dividing it. That's, if you note, in column K, the heading that I copied pasted from the textbook is dimensionless pressure over delta pseudopressure match point. This is delta time over T sub D, C sub D match point. So I have real over dimensionless, and then I have dimensionless over real. So here I should multiply, and here I should divide. Okay? Now, that's not going to help me with my problem over here. But at least I have the units right. And if I have delta T over, I should multiply by that number. Yes? RWA? No. But that'd be worth trying. You're thinking. I'm still not getting anything close. So let's go the other way and let's calculate our match point. The match point that we'd calculate, delta T over T sub D, C sub D match point would be my CD. Let's write this down here. I've got some error here, but we got 10 minutes to figure it out. Okay. If I'm going to solve this equation, I am going to solve for the last term in parentheses. I'm going to start with the CD that I calculated. And I bet you that's my problem. I bet you that number's wrong. Do it with what? Solve what?
If you want, you can set it where you change your perm by adjusting that.
I'm happy with my perm.
No, the other one.
I got my perms match.
I mean the CD, sorry.
I'm trying to figure out where I'm going wrong. My best guess is that 9.14 is miscalculated.
I'm just saying you could solve it quick.
That's not solving it with solver is not going to help me find out where I've gone wrong. I'm going to try to solve for my match point. The match point I'm getting right now is whatever I got up there. And I want to see if I use that, if I'm totally wrong. If I'm totally wrong, then I must have a problem with that equation right there for C sub D. So assuming C sub D is right, I'm going to multiply by 5 mu C sub T R W squared. And divided by divided by 0.0002637 times K. Which is buried, isn't it? I'll just use let's see if I hit it. I didn't hit it. I missed it. Okay, and right now I'm using I'm getting a pretty good match with 0.5 and I'm getting 0.02. If I was to use this number, what would happen to my type curve match? It's way off, okay? So I've definitely got a problem on this aspect. So I'm going to put my type curve back where it is. Let me zoom back in for you. I didn't have any problem when I was doing perm. You know, I had a 10% difference in it, and I was able to get just as good a match in getting the perm rectified.
What is there, like we know when obviously we found two different firms, you know, 0.028, your other one say 0.31. Are those good enough? Are those?
I would say I would even hone in some more.
And which one do you trust more, the one from the Horner plot?
Ideally, I would find 3 or more of these data points right here that were on 0.5. I would use exactly them. If they're on 0.5, that means I've got those data points should be pseudoradial flow. Right now, I'm using everything but the last 2. I'm thinking I should back off maybe 3 more. Okay, since you asked that question, let's just do that right now. I'll worry about my other problem later. Let's take my slope and knock off 3 more points. I'm going to bring back 31 to 28. That'll do something to my perm. 285, and I got to do the same thing to my slope. There shouldn't be a degree of confidence that's different, but you can see how if I just rushed to judgment, I would have used all those points on a linear regression on my Horner plot. Now I'm starting to doubt a little bit whether it doesn't dovetail down, showing some boundary dominated flow. But you can see at this point in time, I'm not making huge significant changes. Did I finish this? Where's my, okay, it should be phi mu c sub t rw squared divided by 000267k. See, I am getting a totally different number for here. So where is my c sub d equation? I probably parked it, thinking I was done with it. Here it is. QT over phi h c sub t. There's no mu in this. I may have made a mistake there. No, I didn't use a viscosity. I don't want to spend any more time trying to figure out what that problem is. There's one other thing we can get from our type curve. And right now, again, I have the best match I think I can get. The only thing I haven't gotten resolved from some equation here is wellbore storage, which is not largely important because it's not a reservoir formation problem. It has to do with the length of pipe I got in the ground, okay? I should be able to measure it. It isn't a huge problem in my analysis. The one thing that we haven't done is we haven't looked at this C sub D e to the 2s. Here's my final check. I have a skin. This will tell me right now which C sub D is. I would have to guess right now that where I've got clicked over is my right C sub D. Let's do C sub D e to the 2s. Okay, I have two C sub D's, don't I? The one I'm back calculating from my type curve mesh and the one I'm calculating from my unit slope line. Equals C sub D times EXP to the 2 times my skin, which I'm going to F4 because I'm going to copy this under both numbers. So 1 or 56. Now I have to really blow this up here because on my blue line I should be on one of those two numbers, and I'm not going to be able to tell which one I'm on because the scale is really tight here. So C sub D e to the 2s, below it looks like it's 10 to the 2 might be above it. Let's count down. 1, 2, 3, 4, I'd almost have to print this off, but it looks like 100 should have been my C sub D e to the 2s. Oops. And that 56 is probably the better number for that, and that's what I'm getting from my match. I think I've made some kind of error in my, how'd that get so small? And my calculation for wellbore storage manually for my unit slope straight line. And I may have picked the wrong equation that didn't account for the fact that I was using pseudo pressure and not apparent pressure. I'll check that. But I think if you look at your textbook, this is the last example for radial flow. From here on out, it goes into linear flow. We'll stop here. I'll pick something that looks like one of the, you'll do well on next week's test if you can work all the problems on radial flow at the end of the chapter. So this chapter is divided from radial flow into linear flow, and the problems are likewise divided from radial flow to linear flow. You'll get one or two problems that look very, very similar to the homework problems, the exercises at the end of the chapter. In general, you will be using a type curve. If for nothing else, to display your results. And in the meantime, I'll try to send you an email after I rectify what my disagreement between the two wellbore storages are. The one that works is the 274. That works with my time. And for some reason, the one I calculate from the unit slope straight line seems to be an error. I'll put something on the news page that addresses where I've made my mistake in my lecture tonight on that.
Dr. Kyle, will this be a test like in your project eval where we'll come in, will we get an Excel file with?
You'll get, yeah, there won't be any paper.
Oh, right, but you'll have an Excel file like on D2L that we
Yep.
already have on phone?
Yep.
We'll do the test on that.
Yep. And there'll be a Dropbox to turn it in. Question?
Yeah, early when we first started going through chapter 6, we covered a few different methods of analyzing the data and coming up with the permanent scale. It was never really clear to me exactly which method we should use for which.
This is a very good question. You need to have, it'll be open book, but you need to have a good idea of if you're using a variable rate drawdown. We've looked at that. The only real differences in the equation, if you have a variable rate, it's built into the superposition function, so there's no Q in your perm term. Okay? At first blush, all the perm and skin equations look exactly the same. But the difference between drawdown and buildup I went over a little bit last week is you got a piece of PWF versus a piece of 1 hour. And that is critical. You cannot mismatch a buildup skin equation with a drawdown skin equation. You'll be looking for the wrong terms. So I would look at all the examples that we've looked at, that we've done in class, and kind of have a table of for yourself, because the tables in the textbook are unwieldy because they have pressure, pressure squared, apparent pressure, and then finally pseudo pressure. But only in the pseudo pressure tables then do you want to be able to differentiate between buildup and drawdown. That's major. And for drawdowns, the first two drawdowns we looked at were variable rate drawdowns. And in the variable rate drawdown, that first term in the skin equation and the first term in the perm equation are different because you're building rate into your time function.
Okay, so if we have a variable rate, we're going to want to use a superposition function.
Yes.
And variable rate and multi-rate are the same thing?
Yeah, I wouldn't use the term multi-rate, but variable rate.
I've seen that book, one of the problems called multi-rate.
Okay, I would call it variable rate. Rate is not constant. The problem we looked at tonight, the rate was constant. Any other questions? Okay, I'm the only one with homework. I have to rectify the C sub D discrepancy. Yes?
The margins are not perfectly made for factors. Derivative part of the is not matching with the.
You want to know why? I would try some things. One is maybe my pseudo time is not good. Let's just use real time. So let's, oh, you know, one thing we didn't do here is what happened to Agarwal's time? Let's use Agarwal's time. You see what I just did? Wow.
Now we can calculate the CD term, probably.
I don't think so, because that affected late time. But that's an important improvement. I'm still in the recorded lecture, but I didn't use Agarwal effective time in my pressure time semi-log derivative. Now this looks a lot better. Remember how I was lopping off points? I should use the last 1, 2, 3, 4, 5, 6, 7, 8 points. 6. So that's 27 through 34. You know, I haven't, in the last hour, I haven't changed my perm. But I think that last thing I did resolved that I do not have a boundary. Now, yeah. It shouldn't make any difference. I can prove that to you.
I was just wondering if it did, because it doesn't, I tried both, I was just wondering.
You know, you're subtracting a constant term. It can't change the slope. But the one thing I could do is, again, I could change this to radial, but at the early time, the difference between Agarwal's effective time and real time is negligible. I don't think there's anything wrong with my slope. I'll just look at it, and it'll dawn on me. Sometimes you just can't do things in front of the. But I am glad that I picked up on the fact, this bothered me too, that I was dovetailing away from that. See, now I got a nice infinite acting radial flow that verifies that I have middle time region data. Okay, I'm done recording.
Now the probability would be got from the type of imperial matching with the
Well, our dimensionless pressures through here should be really at 0.5. See, look at that. See, that our dimensionless derivatives are right at 0.5.
What did you change to get the line on the 0.5?
I was using real time instead of Agarwal effective time for my derivative. See, I took all this time to calculate. Remember, this has the biggest effect at late times. So I was using my pressure derivative, and part of the problem was you see, now I'm using Agarwal effective times, and I was using just pseudo time adjusted times. And that has a big effect at late times.
The values of the P match we calculated for P match and T match, it depends upon which part of the build-up data. It is after the early time region, or it accounts for the entire data.
Yeah, the match is just a vertical match. That solves for perm. Perm and where you're lined up north-south are integrally involved. Your skin and your storage affect your X match.
Some people directly estimate the value of skin by noticing the gap between the pressure curve and the derivative curve, because it is showing the permeability.
Well, that's true, because look, you have this family of C sub D e to the 2 S's.
Yeah.
Okay, so the difference between those two things right there have increasing C sub D e to the 2x. Yeah, that's absolutely true.
Interpretation.
Huh?
It's a kind of quick look interpretation.
Yeah.
If you got the data and you can.
We don't do anything quick in here. Because hopefully by really manipulating the data, you get an idea for what's going on in the reservoir.
Will we also work on the type curves? Those will account for the boundary in the coming classes.
No, but if we see a deviation on a type curve, when we do a radius of an investigation, we don't use the last data point, we use the last data point that's still an infinite acting. So we can calculate the distance to a boundary.
Can we have radius of investigation from type curves?
Yes. If my data did deviate from I would see it on my type curve. Then I would select this time or the time associated with it as the time to use my radius of investigation equation.